Hello. So today, as usual, I will do the coding practice. Okay, so today's question is on the heap data structure. Okay, so that being said, let me get started. So here's the today's question. So you were given an array of CPU tasks, each represented by letters A to Z and the cooling time small n. Each cycle or interval allows the completion of one task. Each cycle or interval allows completion of task. Tasks can be completed in any order, but there's a constraint. Identical tasks must be separated by at least n intervals due to cooling time. Let's see. Return the minimum number of intervals required to complete all tasks. Okay, I see. So let me start with clarifying the interface of the method I will be implementing. So in this question, I'd like to return the minimum number of intervals required to complete all tasks. Okay, mini intervals. And I will be given an array of CPU tasks, and I will be given a cooling time n. Oh, cooling time n. Okay. Okay. And then I will return the minimum number of intervals required to complete those tasks. Okay, I see. Makes sense. So let me clarify the data input and argument. So task is, as described in the question. So array of chars capitalized A to capitalized C. Okay. And also for n, this is the cooling time. And so I will define the data input in this practice by myself. So I will define this as 0 or larger integer. Okay. So tasks can be an empty array, and in that case, I will return 0. And cooling time can be 0, and which suggests that I can execute the same task in a row. Okay. I will read. So this is one of the kind of edge case. Okay, so that being said, I have clarified the interface and data input. So I will think of this question with some examples. So the first case I will be thinking of is I will think with this. And also n is say 2. Okay, let me think with this. So in this case, so what happens is that, for example, if I start with task A, because of the cooling period constraint, I need to separate. Okay, I have to skip A for 2 intervals. So next and second next can be A. However, after that, I can choose A. So this is, the basic constraint by the cooling time. And so that being said, my intuition is that I should choose the task which is remaining, which remains the most. Yeah. So in this case, A has 2 remaining tasks, and B has 3 remaining tasks, and C has only 1. So probably I should choose B first. Then here, okay, let me change my example. Let me go with this. So firstly, we have 4 B's, so I should choose B first. And then next, I don't, yeah, I have 3 B's. Okay, let me write it down. So firstly has 2, B has 4, and C has 1. So when I first choose B, the remaining should be 3. And then I'd like to choose B again, but because of the cooling period constraint, I can't choose B. So I will write it down. So I can say I can choose A first, but I didn't choose it. Let me write it in this way. So firstly, I chose B. Then because I chose B, I have to have 2 intervals for cooling period. So which suggests the next can be 3. Then from here, I will write the time here. Okay. Then from here, for the time 1, I'd like to choose B because it has the most number of tasks, but I can choose it because the next possible time of the B can be 3 or later. So the second largest, the task which remains the second most is A, so I will choose A here. Then, because I chose A here, the next can be 4. Then I have C, which remains only 1. This is the only task I can choose now, so I will choose this, and this becomes 1, 0. Yeah, so I have no remaining C, okay. Then from here, I can choose B because it has the remaining, it has the most number, of remaining tasks. So I will choose B here. Then this is count is decremented by 1, and next can be now 6. And then for time 4, I can now choose A. So yeah. Okay, so I will speed up. So this is 7. Okay. And now I have 2 B's, but how I cannot choose it. So I will skip this. And here I will choose B, and B has only 1, and it is now 9. And for time 7, I can choose A. And the good thing is that I have no A anymore. So yeah. And next I have only 1 remaining B. So I have to wait till time 9. So I don't choose anything here. And then I will choose B here. Okay. Yeah. So this is the algorithm probably I can use. So the rule of thumb is choose the most, okay. Choose the task type which has the largest rim count, and so okay, I'm not 100% sure this rule is correct or not, but let me just clarify. Let me write down the rule by my tuition, then I will justify if it is correct, yeah, or not. Okay, so I will get remaining count. No, I mean, I will, if there are two task types which has different counts, I should choose, one which remains more. Then if the remaining counts are the same and tie, I will choose the next possible time is smaller one. Okay, so I can write it in this way. So largest rem count, remain next possible time. Wait a minute, so which is better? Smallest next possible time or largest next possible time? Wait a minute, so next possible time. Oh, sorry, so I was totally wrong on this discussion. So if the next possible time isn't 0, I mean, if the, I mean, so for every time, I should choose a task which has the largest running count. So definitely I cannot choose one which has the larger next possible time than current time. Out of the tasks with whose next possible time is T, choose a task type which has the largest run count. Yeah. Okay, so the idea behind this rule is, okay, so I mean, I'm still not pretty sure if this rule is correct or not. So I will think if this is correct or not. And the basic idea of the rule of this greedy approach is, so I like to do the task which remains the most, because maybe, I mean, obviously I have to have the cooling period after choosing it. So probably this isn't the, I mean, strictly correct justification, but just, I mean, let me show you the, yeah, intuition of mine. So if I have AAB here, I have two choices. Okay, and is one. Let me think with this. I have one choice that I choose A first, and then for A, next time is the cooling period. So I can choose B, then I can choose A next. So this is a very, successful way of choosing the task, because I have three tasks and I could finish with three intervals. However, in here, if I choose B, which has less remaining tasks than A. From here, I have remaining 2 A's, and I will choose first A. But I cannot do A in a row. I have to have one cooling period. So I have to do A after that. So in this case, it took 4 intervals, which is longer than 3. So the reason of this is that I couldn't make use of the cooling period of A. So I should make most of the cooling period after doing one task. And yeah, so that's why I'd like to choose the most remaining task first approach. Yeah. Okay, so yeah, okay. Then, so okay, I will go with this rule. So okay, so Remy assumes okay, actually so Remy estimates the time complexity and bit complexity. So in this approach, I did the iteration by every interval until I find all the tasks. Oh, and also I have to think how I can choose. Okay, so but before, I mean, before the complexity analysis, I have to clarify how I can choose the task which has the largest remaining count. So the challenge here is that the new task is task is pulled out of the data structure for every time, and also new task should be put into the data structure every time. Yeah. So I have to choose the largest one every time. So probably the heap is the best structure here. Okay. Next possible time. Anyway, but if I use the heap, I'd like to guess the largest remaining count. So probably key of the, yeah. Wait a minute. So, but the challenge here is that I have to make sure that the task which I pull out of the heap, popped out of the heap, has the time which is larger than or equal to next possible time. So keeping track of next possible time is not so hard, I think. I can use the hash map for, hash map of task type to, next possible time. Yeah, so probably I can use the hash map to keep track of this. However, how can I pop out only the task which has the next possible time? Let me think. Okay, so one of the approach I've just come up with is that I will use two heaps. So one of the heap is the this holds tasks in the cooling period. And also I have another heap which has tasks which can be executed. Yeah, maybe it after the cooling period, or maybe it hasn't executed at all before that. So for such tasks, I will fit them in the heap. So, okay, so I will name this. So and also I will call it cooling tasks, which is heap. Okay. And also I will be, keep track of the task which can be executed. So yeah. So these are the data structures I should be using. So the basic algorithm I can use is, so for each time, so revive tasks in coolings and executables, then choose if there are, and choose one task from executable if there is, then wait me coolings next times. Okay, so basically I don't need next times hash map because I decided to use two heaps. So I can, yeah, I can keep track of the next time in each element in the coolings heap. And also, as long as the task is executables heap, I don't have to take care of the next possible time because it has the, it's now executable. So I don't need this. Okay. So then, yeah, in this way, I can return the time taken. Okay, so yeah, I think this works. So let me assume do the complex analysis. So for time, so it totally depends on the time it takes to execute all the tasks. Yeah. So in the worst case, so think of the case when there are only one type of task A, and the cooling period is, say, okay, yeah, sorry. there is only one task type A, and there are 108 tasks, and the cooling period is 5. So in that case, it will take 6 times 100 time approximately. So yeah, basically I can say in the worst case, it takes this long. And for each time, I will pop out of the heap and also push it into the executable heap. And the thing here is that the size of the cooling heap and executable heap never, the sum of them never exceeds the given ranks of tasks. So yeah, if all the tasks is in one heap, it will take log of run tasks time to execute it. Yeah, so this is the worst case scenario. Maybe I can amortize it, maybe. Yeah, I'm not 100% sure of this, but it takes at worst this time. And for space complexity, it will take L because of L because, as I said, I have 2 heaps, cooling and executables, and both of them can be at max length of the tasks. So that's the space versus space complexity. Yeah. So I'm pretty sure that I can optimize this. So the thing is that I took a look at every time from 1 to, and times L. However, I don't have to do it because I have to take a look at every time, which, so, okay, so yeah, what I mean by optimization is so if I have, say, task A and N is 2 or N is 3, so in this case, I don't have to do, take a look at each time in this way. Instead of this, I can okay, so if there is no executable, okay. So yeah. So just think that I finished the execution of the first task A, and then at time 2, I have no task executable, and also I have only A in the cooling period heap. So in this case, I can skip to the next minimum earliest executable time or earliest next end time. Okay. So in this way, what I can say is I don't have to take a look at each time. I just have to take a look at the, for each task, I have to think of the, okay, so what should I say? For each iteration, I can find the, for each iteration, one task is get started. Or revived from cooling period to executable. So the total number of steps should be, so L, yeah, or I should say 2 times L times log L, which is L log L. So yeah, this is the optimization I can make on this. So with this in my mind, I will do the implementation. Okay. So firstly, I will write the test. So let me start with the edge case. So when there is no task, in this case, this is empty, and say this is 2. In this case, it doesn't take any time, so I should return 0. And also some edge case, which is possible is, because there is cooling period where no task is executed. So I will clarify it. Yeah. In this case, it will take this much. And then I will think of the case where there are multiple tasks, because I thought I use this example. Maybe I can simplify this. So this is actually the typical happy path. So in this case, it should take, first I should take B, and I should take A. I will do nothing, send library to B again. Okay, so it will take actually 4 intervals in total. Yeah. Good thing is that I could do task A in the interval, cooling interval of B. Okay, so let me work on the implementation. So firstly, I have all the tasks in the heap. Oh, wait a minute. So in the executables and coolings, I have to keep track of the count of the remaining tasks. So this should be something like each element of the heap should be task in the cooling. Next area is time and random count, and also the same for executables. Okay. Okay, so I will go back to line 64, and I will initiate the first executables list. I will use counter with the tasks. So in this way, I can get tasks and count. Oh, and sorry, and also I have to keep track of main count. It means so the main next area is time. Oh, sorry, this is I have to get remaining count first. Then I will get task type. And for coolings, I should get the earliest next of time, and we get task count. And also probably I need remaining count. Maybe I can use the data structure for each element in the heap. However, for now, I think I can just use a tuple for this purpose. Okay. So in line 64, I will count the tasks, and what I should get is for each task and count, remaining should be count, and task type should be so task. Yeah, so this is how I get the initial coolings and executables. So I will start with time 0. Okay, yeah. So if there is any cooling tasks or executable tasks, I will take a look. So the first thing I have to do is, yeah, revive tasks. So if there is any cooling tasks, and the first element is the heap, which is the earliest next possible time of each task in the cooling period. Heap is larger than or equal to current time. I can revive it. So I will pop it out. So next possible time. Actually, I don't have to keep track of the next possible time. Type and remaining count. Then I will revive it in the executables. So remaining count and type. Then next thing I have to do is choose one task from executables. Yeah. So if there is a tree, I will get remaining. Yeah, okay. So, because this is executable, I can pop it out. Okay, so this is how I get the remaining task. And then I have to do this task. And so doing task means I should decrement the remaining count. And then if there is at least one remaining count, I will keep push to the type in the previous. So the element of the cooling is next possible time, task type, remaining count, time plus cooling time. Plus one, because I have to, yeah. N is the, interval of the cooling period. So yeah, is there, say, two cooling intervals? What I can, the time I can do the same task again is, I mean, I have to increment 3. Oh, yeah, on this time. Also task type and also remaining count. Yeah. So I will push this into the heap. And as I said, I have to, move the time. Oh, this should be while loop. Let me do it in this way. So, and if there isn't any task, I will break and return time. And otherwise, I will, go to the next time possible, next event of the time. So Okay, so what I can do is if there is any executable remaining, I will just increment time by 1 because I can do the task in the next time. I mean, 1 second later. And otherwise, there is a because there is at least one cooling task. Okay. Time should be first cooling task and next possible time. So it should be 0. Okay. Yeah. So in this way, I think I can go to the next time possible where any of the event happens. Yeah. Event, what I mean by event is reviving or doing one executable task. Yeah. Okay. So let me quickly check with this no task case. So I will work through my code. So here in this case, cooling is empty array, executable is also empty array, and I will start with time 0 ending in line 68. So this is, yeah, I go into while loop, and in line 70, this isn't true. So I go to line 75, and also this isn't true because executables ranks is 0. And oh, oh, yeah. So I fix the index of line 78 to 81. I will do the task if obviously when there is a task executable. Yeah. Okay. So in my case, length of the executable's list heap is 0. So I don't do anything and I go to line 83. And this is true. Both of them are 0. So I will break from this while loop and I will return time 0. So this test case, line 97, is met. True, pass. Okay. And for the test case line 99, I will quickly do this before I check the line 101, which is more complex case. So in this case, I will get executables as task A2. So like this. Okay. And I will start from time 0. And in line 70, there isn't cooling task. So I go to line 75 and yes, there is a executable task. So I will pop it from the heap and this becomes empty now. Heap becomes empty now. And in line 79, remaining count is incremented by 1. So now it is 1A. Because there is at least one remaining count, I will push it into the cooling period. So the current time is 0 and n is 2. So the first element should be 3. So cooling should have 3 and task type A, and remaining count is now 1. And I go to line 83. So still there is a task in cooling, so I don't break. I go to line 86. And here, because length of the executable is 0, I go into line 89, and cooling 0 is now 3. So now time is 3. So I warped 2 times 3. Okay. Then I go back to line 70, and because there is one task which is cooling, so I will, yeah. And also when I take a look at line 70, cooling 0 is now 3, which is the same as the current times 3. So I will pop this element from coolings. So it should be 3A and 1. So I will push this into the heap executables. So now it has remaining count is 1. A. Okay. Then in line 75, there is one task executable. So wait a minute. So now time is 3. 0, 1, 2, 3. So yeah. So oh, wait a minute. So yeah. So okay. In line 75, I will pop this element. So I will pop out 1A. Then remaining count is now 0. So I don't go into this line 81, and I go to line 83. And because the task is already popped out of executable, the rank is 0, and also cooling, this is now 0 because I popped it out from line 71 and pushed into executables. And immediately after that, I mean, yeah, this task was executed. So now in line 783, both of the ranks are 0, so I will break. So I will return 3. So there is a mistake in this test case. So time, which is defined in line 66, signifies the current time. So I mean, I should say the clock time of 0, which begins from 0. So what I have to do is I have to add 1 to this time. Wait a minute. So if there isn't any task, okay, I can just return time here, which is the current. No, because there's a time as 0 index. I have to fix this to begin from time 1, or I should say interval 1. Then if there isn't any task, I will return the current time. Yeah, and I actually don't need this. And because I started with time 1 here, So I have to early return if rank task is 0. I will return 0. Yeah, okay. Because I started with time 1. In this blind 99 case, it should return 4, which is expected. Okay, so I'm a bit tired, so I don't walk through the last case. I will execute the code. I fix the syntax error. I fix line 63. Oh, here. In line 75, executables. Oh. Unfortunately, it seems like it went into the infinite loop, so I have to fix it. So let me think why it is, this completed runtime. No, I see infinite loop, definitely. So let me just check if I just execute only line 99, line 97 test case, it's okay if I choose only line. Oh. Okay, so line 99 test case has the infinite loop. So let me think. Push pop ranks, coolings, ranks, executables. Pop executables. Keep pop coolings. Okay, I see. So this has to be smaller than current time. Because obviously coolings has a time which is next possible as the first element of the tuple of each element. So when it is smaller than, earlier than the current time or the same, I can pop it out. Oh no. Wait a minute. So time is 1. Let me start with coolings and executables and current time. And so because I have to break I'd like to break from the while loop. I will return. Okay, so here I can see the, content of the heap, so I can check it. So okay, it seems like the count in the current heap isn't decremented. Ah, I see. So in line 92, I have to decrement by 1. Okay. Okay, good. So I will also execute the test of line 111. Oh. So I got assertion error. Okay. So basically, now I can, yeah, I can take a look at this again. So executable is 2A. Wait a minute. So I will command out the first two test cases. So firstly, I have 1A and 2B, which is okay. And then, oh, it does the, I see. Okay. I have to do the task which ruins the most. So here, I have to use the negative number of count because Python heap q doesn't support max heap. I have to negate the element to use it as the max heap. So in this way, and when I push to the executables, I always negate it. And when I pop it out, I have to negate it. Let me try with this. So now I get, okay. So firstly, task A is executed at time before time 2. So this suggests that the task A was done at time 1. Then at time 2, this B is executed and it has cooling. Wait. So still this isn't correct because I'd like to do the executable, B first. So executables. Okay. I have to heapify this. Okay. So let me try with this. Okay, good. Seems like the test passed. So I will revive all the test cases, and also I will command out the print noisy statement. Okay, good. The test passed. So, yep, I will execute this in the LeetCode platform. Okay, so it accepted. Yeah, it was a bit tiring task, but it was okay that I could finally finish it. Okay, so bye.